Hello? No, guys. Hello? So within the perfect metal, we cannot have E field, and also we cannot have charge distribution. But when we have a metal dielectric interface, we can have some charges being deposited on the interface. But due to the fact we have metal underneath, we can only have normal E field lines. We cannot have tangent E field lines. Why not? Because if we have the tangential E field line inside the metal, we cannot have E field. So curl of E equals to 0 must apply across this boundary. So we cannot have the tangential E field line. We can only allow to have normal E field lines. Today we're going to continue to explore about metals. In this case, we have a metallic shell. So the shell is spherical. It has an inner radius, Ri. I represents inner. And the outer radius, Ro. All right? So this is what we define as the metallic shell. And somehow, fictitiously or magically, we can put a charged cube inside the shell. And we want to investigate how the shell is responding to the presence of the charge, right? So we are going to look into the charge distribution on the metallic shell, and we are going to derive for the resulting E field intensity, as well as the electric potential. But first thing first, again, for this given geometry, which orthogonal coordinate system should be used? The shell is spherical, and the point charge emits field lines in a radiant way. So the preferable coordinate system is, again, spherical coordinates. All right? So we are going to use spherical coordinate, and we are going to use Gauss's law, because we have a very symmetric geometry. So let me walk you to the board, but before we do that, we are going to discuss and analyze this problem into 3 different spatial regions. The first one is, my observer is outside of the shell. I'm going to invoke Gauss's law. Second region is, if the observer is within the shell, magically, don't ask me why, but if you have an observation point inside the shell, then the result should be very different as compared to outside of the shell. Third region is when your observation point is inside the shell. Right? So we are going to classify the analysis into 3 different spatial regions: outside, inside the shell, and within the shell. Right? So let's walk to the blackboard and ask ourselves, well, because you have forced a charge into the metallic shell, I'm only drawing a cross-section again. So we know that for a given point charge, we assume it's a positive charge. So it emits radiant E field lines. That has been known for the past 9+ hours. Right? So ask yourselves, When you have field lines, they start from positive charge and somehow they end on the inner radius of your metallic shell. What is that going to do to the metal? Well, you know that along the metal dielectric interface, you are allowed to have charge deposition, right? And that resulting induced charge can have normal E-field lines. So it is proper for us to draw some induced charge depositions, okay? Now the sign of the induced charge must be negative. Why? Because E-field lines starts from a positive charge and terminates at a negative charge. So this is telling you, initially, if you only have this metallic shell, its charge is neutral. Being metal, it has a lot of free electrons, but it's uniformly distributed. Now, with the presence of your charge, the inner shell will have a lot of induced, or you're trying to redistribute the electron profiles. So the electrons will be attracted by this positive charge, so the entire inner shell will be covered with lots and lots of electrons, right? And the sum of all these negative charges would be Q, but having a negative sign, right? On the other hand, as I mentioned, the metallic shell started as a charge-neutral material. So the charge needs to remain neutral. What does that mean? That means currently your inner shell is having a lot of electrons. So seemingly this metallic shell is now negatively charged. But that cannot be true because initially it was started as a charge-neutral device. So at the same time, you need to have positive charges deposited or dispersed on the outer shell. Okay? So you have one induced electron, you have one positive charge, right? So overall, your metallic shell remains to be charge neutral. So I'm going to use the yellow color to denote all these positive charge densities adds up to Q. All right? So without the central charge, this metal is just everywhere charge neutral. But having this charge, the inner radius, the inner sphere, is filled with negative charges. The outer shells are filled with positive charges. But overall, the metal itself remains charge neutral if you add the charges all up. Right? So now let's try to analyze this system and its resulting E-field intensity. Because this geometry is perfectly symmetric, so using Gauss's law is the smartest choice. So how to invoke Gauss's law? If I have an observation point or an observer here at P, how should I invoke Gauss's law? Gauss's law tells you if you form a closed surface. You form a closed surface, and you're trying to ask yourself how much charge is being encompassed by this surface. And then those charges give you the E field intensity. So if I'm standing here and I form a closed surface, like a sphere, right? I have a spherical surface touching this P point, is closed, and I ask myself, hey, there's no charge inside, so at this point, there's no E field. Is that correct? That cannot be correct, right? Because the problem we're trying to analyze is due to this charge and due to this spherical shell of metal, what is those combination going to affect my observation point? All right. So somehow this closed surface needs to include the sphere, the shell, and the charge. So I should be using a very big sphere, right? I should be using a very big sphere. So the radius is r, right? Starting from the charge all the way to my observation point. That's my radius. And I have a very big closed surface to include the charge as well as the shell. Now, for this case, right? So I know that somehow, due to spherical coordinate symmetry, all the field lines are radial, and I know the surface area is 4 pi r squared. And then the question is, for this closed surface, how much charge is being encompassed? Well, let's count. I have my initial charge, right, Q, and I have all this induced negative charge, which adds up to negative Q. And then I also encompass all these induced positive charges, which adds up to Q again. So basically, you have Q minus Q plus Q. Take a good look. So this is telling you, when we're standing outside of this shell, when we're outside of the shell, the electric field intensity being felt at the observation point is exactly identical to just having the charge. So the shell is really doing nothing, right? You still remember this result, right? Q over 4 pi epsilon 0 r squared is the E field intensity for a single charge. So this is actually telling you, having this shell or not, there's no difference. Okay. All right. So that's case number 1. We're standing outside of the shell. What happens if we stand inside? If our observation point is inside the shell, meaning the radius r is greater than ri, is smaller than rn. So now I can form a second closed surface, right? So then the question is, how much charge is being encompassed by this closed surface? You have the initial charge at the center, and you included all these induced negative charges, which adds up to negative Q. So Q minus Q is 0. And this tells you, well, Gauss's law tells you, as long as you are within the metal, you don't have net charges. Well, the net charge sums up to 0. And therefore, you don't have electric field. This is not very contradictory because, as we mentioned, for ideal metal, inside the metal, you cannot have E field, and inside the metal, you cannot have charge distribution, right? So this is not very surprising. Inside the metallic shell, you have no field. So this is a very nice demonstration of using Gauss's law. It's so simple, right? You don't really need to perform integration. You only need to take account of the net charge enclosed by your surface. All right, so that again tells you if you don't have fields, the entire shell is having a constant potential, right? Constant potential. Now let's walk inside towards the center. So now we're really within the shell. Within the shell, you can form another closed surface, which is also a sphere, but having a radius smaller than Ri. For this case, for this closed surface, you only encompass the initial charge, Q. So again, your E field is non-zero. Again, it's like Q divided by 4 pi epsilon 0 R squared. It conforms to the E field intensity of a single charge again. So the effect of this metallic shell is very apparent. Within the shell, there's no effect. Outside of the shell, there's no effect. You cannot really tell the difference you have the shell or not, within or outside of it. It's only really inside of the shell you feel its presence because you don't have E field intensity, right? So outside of the shell, within the shell, you have well-defined E field intensity, which obeys to Coulomb's law, right? It's somewhere within the metal. Suddenly, you have abrupt field jumps all the way to 0. Okay, so this is the entire profile of the system, the charge plus the metallic shell. So once we have the E field distribution, we can just perform integration, line integration, to retrieve the electric potential. We only have to perform integration, right? So we start from outside. Infinitely far means potential equals to 0. We integrate all the way up to here, RO. So when we're outside of the shell, the potential is Q divided by 4 pi epsilon 0 R. Again, identical to a single charge. So with or without the shell, doesn't make any difference outside, right? For this region, within the metal, because you don't have E fields, so there's no need for you to perform the integration. Integration of 0 means 0. So this entire region within the shell, within Ri and Ro, you have a constant potential. And that constant potential is Q divided by 4 pi epsilon 0 Ro. Right? So for the entire metal, you have a constant potential. Okay? For the region inside the shell, we can perform integration. But again, when we perform integration, the most important issue is in integration, you always need to add a constant. And that constant for the inner region is the potential of this region. You need to add it up, right, during integration. So the result is slightly complicated, right? For a test, whether you obtain a correct result or not, for a test, you should be able to insert the R value to its particular value to see whether it makes sense. So in this case, when we're trying to derive the electric potential as a function of space, we are most interested in R equals Ri. It needs to reduce to this result. Okay, so R equals Ri, these two are canceled, so the potential is Q divided by 4 pi epsilon 0 divided by Rho, which makes sense, right? Which converges to this constant potential. And this potential is equal to the potential of the outer region at Rho. So everything makes sense. But let's try to talk in more details. This is a very simple case, but it contains a lot of information. First question to you. Well, as we mentioned, by default, we almost defined within a perfect metal, we cannot have electric field. And in this case, indeed, there's no field within the metal. But why is there no field inside the metal? Take a good look at the picture I drew. Take a good look at the induced charges on both metal-air interfaces. At the inner surface of the shell, I have induced negative charges, right? And due to charge neutrality, the outer part has positive charges. So to answer why within the metal you have no net field, it's very simple. Let me use another color to see whether red appears good. Okay. If you have this positive charge and you have the negative charge, how can you just draw the resulting field lines? Well, field lines start from a positive charge and terminates on a negative charge, right? So the meaning of this metallic shell is the induced charges are there so that these charges help to protect the metal being field free, right? This field strength is used to counteract the field strength of this center charge. So you have this is due to Q, E due to Q, and you have E due to the induced charges. So the purpose of having the induced charges is to cancel out your external field strength, right? So inside the shell, you have cancellation, but outside, you don't have cancellation. Okay? So again, outside of the shell, you have field. Within the shell, you have the field. But exactly inside the metal, you have no field. Okay? So these charges are used to cancel out your external field lines. Right? So at this moment, let's talk about some terminology you might have heard. I mean, we talked about it, right? Electric shielding. Shielding, like a shield. You hide inside, you cannot feel anything, right? So let's talk about this case in more details. I think each and every one of you, us, you, including me, have this daily life experience. We're talking on our cell phone, right? As we're talking, we enter into an elevator. We still talk. But once the doors of the elevator closes, probably within 5 seconds, your call is dropped. Right? Do we have this common experience? Have you? Right? Each and every one of you. Why? Think about it. You have your cell phone and you walk into the elevator. As the door of the elevator closes, you and your cell phone represents this charge, right? Let me just erase it. If I know how to draw a cell phone, button, right? So in the past, we have this antenna, but not anymore. So your cell phone represents this free charge, and the elevator represents this metallic shell, right? Usually elevators are made of steel, metal. So why is your call dropped? Because currently, up to our analysis, even though your cell phone enters a closed, sealed elevator made of metal, whenever you're trying to send out your signal, people outside can still pick it up, right? The result up to now is whenever you have a charge installed into the shell, people outside can still sense its resulting E field intensity, right? Outside, you still have E field. So that means when you're trying to talk over your phone, ideally someone outside the elevator can still hear you. But why is your call dropped? So electric shielding by default works in an unfair way. Let's try to draw the elevator. Usually elevators are rectangular. Okay? And again, you have a cell phone. Okay? Now think, what happens if you have a charge outside? The first case is telling you, ideally, when you take your cell phone, as you are talking, you go into the elevator, door closes, so you have a completely sealed metallic enclosure. When you're talking, your cell phone is sending out signals by changing the amount of charge, right? So the people outside can actually sense your charge being increased or decreased. But now let's take a look at the reverse situation. If your friend talking on the phone with you outside of the elevator, right, is donating a charge, what do you feel inside the elevator? Well, again, If your friend is producing a positive charge, it emits field lines. Okay? But this is an asymmetric case. Okay? So overall, when these fields emit, they also induce charges. Okay? And due to the geometric asymmetry, in this case, the elevator wall, the wall of the elevator are made of metal, are somehow polarized in this case. So more negative charges are redistributed towards the right and leaving the left side more positively charged. Okay? Then we form a Gauss surface. So if someone sitting inside, right? I want to ask, what is the field felt by your cell phone inside the elevator due to the presence of this external charge? This charge adds up to -Q. And that tells you when you have external charge, this metallic wall is used to cancel the charge. And therefore, inside the elevator, your cell phone cannot receive the signal. Okay? So electric shielding by default works in a unilateral way. So when you have charge forced into the shell, the field can actually penetrate outside. So people outside can feel the existence of having the charge. But when charge is outside of the shell, people inside cannot feel the presence of the external charge. So inside, your field is 0. All right? So this is a partial electric shielding. Now, as a challenge to the students, this might appear in your second examination. How to make electric shielding using this closed metallic shell so that it's bilateral. What do I mean by bilateral? In the current case, the external field cannot enter into the center. But the field inside the shell can penetrate outside. So my challenge to you is how to make the field inside also disappear. You have the same elevator, right? Currently, only the external signal cannot enter into the elevator. So how can we make the signals produced inside the elevator also vanish outside to make it bilateral or bidirectional? This is my challenge to you, right? Okay, so now we're going to move into a new topic. We have pretty much concluded on the discussion of metal. And now we're entering into dielectrics, insulators. Again, I am going to talk about electric dipoles. As you can feel, I emphasize on electric dipoles a lot, right? So this is the third time we mentioned about electric dipole. Electric dipole, by default, you have positive charge, you have negative charge. They are spaced by certain distance. And then you have electric dipole. In nature, a lot of molecules come in different forms, right? Oxygen that we breathe every day, CH4, that we probably use quite common. All these, due to geometry, symmetry, these are not really dipolar. Okay? Meaning, for O2 molecule, you have two oxygens. So the electrons, they appear over to the right or over to the left. They are quite equal because this bond is very symmetric. For CH4, you have one carbon and four hydrogen atoms, but the way they are formed is a perfect tetrahedron. So the vector sum, so each CH bond is dipolar. You have more positive charge here and more electrons here, but because it's a perfect tetrahedron, so the vector sum goes to 0. So for these two particular molecules, they are not polar. On the other hand, you have lots and lots of molecules. For example, water that we drink every day, H2O. You have two hydrogens and one oxygen. So the way they are bonded is asymmetric. So this is more like, I can say, oh, I have a positive charge, and I have a positive charge, I have a negative charge here. And the vector sum does not go to 0. So in nature, there are a lot of electric dipoles by default, right? And this is looking at our materials in a microscopic sense. We're investigating into the molecular structure. So now the question is, what happens if we have lots and lots of molecules? So we're looking at a macroscopic sense. How can we define, or how can we mathematically formulate these materials? Remember, now we're talking about static electric fields inside materials. So we need to have a proper formulation to describe the materials. And the basis is on how easily polarized materials are, right? So let's look at supermaterial. So microscopically, at each location, you might have dipoles, right? So each white area means a molecular basic element. So it might appear dipolar. But overall, because all these dipoles are randomly oriented, so when you take a step back, you look again, all these, the vector sum of each individual dipole, randomly oriented, again sums up to 0, right? So even microscopic molecular structure might be dipolar. The entire bulk material can be non-polarized. Okay? So usually, the net dipole moment is usually just 0. So now what happens? So in this case, H2 is non-polar, right? Again, they're very uniform, they're very symmetric. So the chance of an electron showing up in the right or in the left is pretty much equal. So it's unpolarized. You cannot say this is more negatively charged, so this is more positively charged, right? You cannot. So this appears like an uncharged molecule, and it's not polar. And now the question is, what happens if we somehow exert an external field? We position this molecule into a special location where you know there is electric field. Again, like our metallic shell case, when you have external field, field lines terminate on negative charges, right? So for this case, I'm pulling electrons from the right to the left because my direction of the external field is pointing from the left to the right. right? So more electrons are attracted to the left atom, thus leading the right hydrogen atom to appear more positively charged. So in this way, you have successfully produced an induced electric dipole. Initially, hydrogen molecule is not polarized, but due to the presence of your externally applied field, you somehow polarize it, right? You redistribute the electron potential to the left. So this appears as a negative charge, and this appears as a positive charge, and they are separated by a distance of d. And therefore, you have a p electric dipole vector, defined as q times d. Okay? So even though you have a non-polarized material, under the presence of externally applied field, you can polarize it. Second case, if microscopically you already have polarized dipoles, under the presence, but remember, even though each individual can be polarized, usually they are randomly dispersed. So under the presence of your external electric field, this external field tends to align all these microscopic dipoles in the same direction. So you further enhance the dipole moment, right? So, for example, you might have a dipolar molecule which is originally aligned in the y direction, but under the presence of an x-directed field, this dipole, this molecule, rotates to the direction of your externally applied field. Okay? So in this case, for polarized material, your external field is used to rotate the molecules, so they are aligned, right? Now, for the last few minutes, I am going to compare the difference and similarities of dielectrics, insulators, and metal. So for example, I have a dielectric material, glass, for example, or silicon. Silicon, yeah, it's also semiconductor. Okay, so glass or sapphire. Okay, crystals. I have in space some externally applied field, and somehow I insert this insulator into this spatial region. What's going to happen? Due to the presence of the externally applied field, I can induce electric dipoles within the material, right? But this material might not be that responsive. So even though I have 7 externally applied field lines, I only induce 3 pairs of electric dipoles. Okay? So now the question we're trying to investigate is very interesting. Materials can produce induced dipoles. It's not magical, it's anticipated. But what is the functionality of those induced dipoles? Ask yourselves. Are induced dipoles there to make the E field strength inside the material stronger than your externally applied field or weaker? Think about it. Let me give you a hint. Take a good look at the metallic shell that we just drew on the blackboard. So what is the sole purpose of the induced electric dipoles? Take a good look at the sign of the charges of the induced dipole. We have applied a downward external field line, so this end of the dipole must be negatively charged, and the other end is positively charged, right? So this remains charge neutral. So in this case, your induced P vector is pointing downwards, okay? So remember, you have your applied field direction and your induced polarization vector is parallel to your externally applied field, which is fine. So your P points downwards. But when you have the downward P, what direction of its own E field intensity? What is its direction? If you still remember the analysis we covered from last class, we talked about electric dipoles in details. Once you have this induced electric dipole, you have positive charge, negative charge, P is defined in this direction, parallel to the externally applied field, but the dipole itself is generating an E field intensity in the opposite direction to the externally applied field. Right? Field starts from a positive charge and ends up at the negative charge. So now, with this figure, are you able to tell me the best way of learning is once you read something, you come up with your own conclusive remark. So tell me, what is the sole purpose of this induced electric dipoles? For materials, we classify materials in electromagnetics on how sensitive this given material can produce induced electric dipoles. Right? So this material is not very sensitive, but once you have induced dipoles, the dipoles generate a counteracting electric field intensity to combat the external fields. So with the presence of this induced dipoles inside your dielectric, the overall, the net E field strength is your external field plus your field generated by the induced dipoles, but they are in a different direction, so they counteract, they cancel out partially. So remember, for myself, my conclusive remark for this part is for materials that can give you induced electric dipoles, they're there to make the overall field strength weaker as compared to external field. Okay? So inside the material, inside the dielectric, the field strength are always weaker as compared to your externally applied field. Why? The induced dipoles produce a counteracting field vector. Right? So in dielectrics, the induced dipoles are used to counteract external field. So let me close with a direct comparison of metal. For metal, you have a lot of free electrons, right? What does that mean? You have a piece of metal positioned in the same external field. Because metals have so many free electrons to spare, one given external field line, you can induce one free electron and making the other end appear positively charged. So that for metal, the way you understand metal is you have a perfect material to induce electric dipoles. Dielectrics are bad metals. The ability to induce electric dipoles in dielectrics are not perfect. Metals, they are perfect. So one line, you produce one set of electric dipole and making the metal to appear as field free. Okay? So this is the reason why metals have no field inside, because they have ideal ability to produce induced dipoles. Okay? So inside the metal, you don't have fields in the static equilibrium sense. Right? So I hope by this direct comparison, you know that metal is perfect. It can just generate whatever induced dipoles you want, but for dielectrics, it's not ideal. Right? But inside the dielectrics, the field strength is weaker as compared to outside. And that weak field is a result of the field generated by the induced electric dipoles. All right, so with that, I'll just conclude for the day. Next Monday, during class time, you are going to enjoy your first examination, right, online. It's actually open book. You're free to use your references and calculator, but you must work on your own. All right, so good luck.